Hello and welcome to the first video on this channel. This is inspired by a Numberphile video quite a few years ago about the number 16. In this video they said that 16 is equal to 4 squared. 16 is also equal to 2 to the 4. And that's kind of interesting because you can swap the 4 and the 2 and it doesn't matter, you still get the same answer. And so, funny enough, 16 is the only number where you can write it as a power and then swap the base and the exponent of the power, and you still get the same result where the numbers are integers. Except, of course, trivial results like 3 to the 3 equals 3 to the 3, which is equal to 27. We don't care about that, that's boring. The number that's the same, we're not interested in that. What I'm going to do today is prove that 16 is the only number which can be written in this way. And so what we're going to be considering is the equation a to the b equals b to the a, where we have a and b are both positive integers, and we have a is less than b. This a is less than b bit encompasses a is not equal to b, and also it means that we don't duplicate our solutions, because we could have a equals 2, b equals 4. We could also have a equals 4, b equals 2. We're just cutting down the number of solutions. I really do wish I had a bigger blackboard, because I'm going to have to do a lot of rubbing out and writing back on again. But this solution actually doesn't require much number theory at all. It's more of a calculus kind of approach. What we're going to start by doing to make it easier to deal with the exponents is we're going to take logs of both sides. And so we're allowed to do that because a and b are both positive, and so a to the b and b to the a must also both be positive. So ln of a to the b equals ln of b to the a. Now, because a and b are both positive again, we can use our log rules to say that b ln a is equal to a ln b. And now we can divide both sides by ab to separate ab into different sides of the equality. And so we have ln a divided by a equals ln b divided by b. So we've successfully separated our variables. And now, this may not look any simpler, but actually it's quite helpful, because if we let the function f of x be equal to ln of x divided by x, we can now say that f of a equals f of b. And so now we're looking for parts of the function of f of x where we can get two x values giving the same y value. We want a 2-to-1 function. So what we want to do now is we want to sketch our function of f of x. Now we don't need to consider the negative side, because for negative x, ln of x is not defined. And also for x equals 0, ln of x is not defined. And we can't divide by x either. But we can consider the function as f of x approaches 0 from the positive side. And so we'll have x approaches 0 here. When x approaches 0, we'll have ln x approaching negative infinity. And we'll have 1 over x approaches infinity. F of x is the product of ln x and 1 over x. And so this means that f of x will approach negative infinity as x approaches 0. And so we can draw that onto our function here, approaching negative infinity. We can also consider the case of what happens when x approaches infinity. So you can kind of think of it intuitively here that ln x will grow much slower than x as x approaches infinity. So the numerator will become arbitrarily small compared to the denominator, and our function will approach 0. Or you can do it a bit more rigorously and say, well, ln of x and x both approach infinity, but we can use L'Hopital's rule here. So we're looking for limit as x approaches infinity of ln x divided by x. If we now differentiate ln x gives us 1 over x, and differentiate x gives us 1. And so this is just the limit as x approaches infinity of 1 over x, which is of course 0. And so we can draw that on now. As x approaches infinity, f of x will approach 0. And so now we can consider the x-intercept and the turning point of the function, and that'll be enough for us to sketch it fully across all ranges of x. So the next part, which is the x-intercept, is fairly simple. The x-intercept is just when the value of the function f of x is equal to 0. And so then we have ln of x divided by x equals 0. And then multiplying by x on each side, we get ln of x equals 0. And therefore x is going to be e to the 0, which is just 1. And so we will intersect the x-axis there at x equals 1. Now, for the turning point of the graph, we want the derivative of f of x with respect to x, of course, to be 0. And so here we'll have to use the quotient rule. So we'll let the numerator ln x be equal to u, and we'll let v, the denominator, be x, and then of course we have f of x equals u on v, and so we can use the quotient rule. So differentiating u with respect to x, we get that u dash is going to be 1 over x. Differentiating v with respect to x, we get that v dash equals just 1. And so now f dash of x by the quotient rule is going to be u dash v minus v dash u divided by v squared. Now we just substitute u dash v and v dash and u into this, and we get that f dash of x is equal to, so u dash equals 1 over x, v is equal to x, and then 1 over x times x, and then v dash is equal to 1, so minus 1 times u, and u is ln x, divided by v squared, and v is x, so this is divided by x squared. Now, to simplify things a bit, this minus 1 times ln x is just minus ln x, and 1 over x times x is going to be just 1. And so, when our derivative f of x is equal to 0, we can multiply by x squared on each side. We have 1 minus ln x equals 0. Therefore, ln x equals 1. Therefore, x is e to the 1, which is just e. And so we'll have the turning point of the function at x equals e. So now that we've sketched our graph of y equals f of x, we know that we're looking for values of a and b where f of a equals f of b, a and b are positive integers, and a is less than b. And so we need two x values distinct from each other which have the same y value. And so these x values cannot be in the range x is less than or equal to 1, because f of x is a one-to-one function for x is less than or equal to 1. So our values of a and b must be greater than x, must satisfy x is greater than 1. Now, if we had a greater than e, then we would have our a somewhere here. Now, f of a would be here, and we have our f of a, and f of a is the same as f of b, so our b must be here. But this would give us B less than A. But we specified that A must be less than B so we can get rid of our repeat solutions. And so A is not less than E. Therefore, we have 1 is less than A is less than E. And now we also know that E is less than 3. Therefore, 1 is less than A is less than 3. Now, A, as we specified, was a positive integer, and so there's only one positive integer between 1 and 3. Therefore, A equals 2. And if we have A equals 2 here, then there is only one other value of B which satisfies the equation. And so B equals 4, which we know works, must be the value of B. And so 2 to the 4 equals 4 to the 2 equals 16. 16 is the only number which has this property. Thanks for watching. Leave a like if you enjoyed, and I'll see you all in the next video. Bye.